All right, chemists, welcome to another lecture in our series of lectures for AP Chemistry. This is Chapter 15, Lecture number 2, in which we will introduce buffers and buffer capacity. Let's get started. All right, so buffer systems are the most commonly encountered complex aqueous equilibria systems which you will encounter over the course of your AP curriculum. The idea of a buffer system is that it is an aqueous system which is going to resist changes to its pH. That is, a buffer system will always have the capacity to both absorb the addition of excess hydrogen ions and the addition of excess hydroxide ions. These buffer systems are commonly encountered in the real world in a number of different places where you may have seen them before. Particularly in the world of biology, in which it's very important to maintain your own homeostasis, that you maintain a relatively constant pH level in your blood, for example, which means that your blood is essentially a system which is buffered to resist rapid changes to its pH. Or another place where you might encounter this is in a place like if you've ever seen like a fish tank. Fish, as it turned out, are very, very sensitive to changes in pH to maintain their own living systems. And as such, it's important that we appropriately buffer a fish tank so that it doesn't experience wild swings in the pH due to changes in the acidity of the tank water. So, the idea again behind a buffer is that it's able to both absorb hydrogen ions and hydroxide ions and thus maintain a relatively similar pH. Generally, the makeup of a buffer system is going to be either composed, number one, of a weak acid and the salt of that weak acid, or a weak base and the salt of that weak base. And again, the key idea is, let's consider for a moment here a weak acid you commonly encounter, something like, let's say, acetic acid. Acetic acid, again, is a weak acid, which means if you were to add hydroxide ions to a solution which contains acetic acid, those hydroxide ions, the strong base, would be consumed by a reaction with the acetic acid, producing water and the acetate ion. And as such, it would resist a great increase in the pH as those added hydroxide ions were consumed over the course of that reaction. Similarly, a salt of that acetic acid would be sodium acetate. That salt sodium acetate contains the acetate ion, CH3CO2 negative, and the acetate ion, recall, is the conjugate base of acetic acid. Now, remembering that acetic acid is a weak acid, that implies that the conjugate base, the acetate ion, is therefore a relatively stronger conjugate base. And as such, that conjugate base would be able to absorb hydrogen ions were they added to the solution. So again, if we added a bunch of hydrochloric acid, that hydrochloric acid would not rapidly decrease the pH of the solution, as the H-positive ions, upon entering solution, would react to that acetate ion, forming the weak acid acetic acid. So again, a mixture of both an acid and a salt of that acid, which contains the conjugate base of the weak acid, would therefore be able to resist changes both to the positive side and to the negative side to the pH of the system. So let's go ahead and have a look here at example number 1, which describes to us here the production of a buffer solution by mixing together solutions of ammonia, NH3, and ammonium chloride, NH4Cl. And let's consider what each of those two species are. Ammonia, as you are familiar, is itself able to accept protons, meaning this is going to be a weak base in our solution. Conversely, ammonium chloride is a soluble salt, which upon dissociation would separate into ammonium ions and chloride ions. Now, the chloride ion I don't care a whole lot about here, because recall the chloride ion is the conjugate base of hydrochloric acid, and as hydrochloric acid is a strong acid, that implies the chloride ion is a very, very weak base and therefore not likely to be able to affect the pH of a solution. But conversely, the ammonium ion, NH4 positive, is the conjugate acid of ammonia. And therefore, this solution contains both a weak base, ammonia, and the conjugate acid of that weak base, which is the ammonium ion, which implies, therefore, this would be an effective buffer system. Now, that being said, let's take a look at what happens upon the addition of either an acid or a base to this solution of our buffer. If we add hydrochloric acid to our solution, thinking for a moment about what the acid will interact with, acids are not going to react to other acids. Instead, the acid will react to the base in our solution, which is the ammonia. So if I write here HCl plus NH3 as my reactant species, as the hydrochloric acid will be a proton donor, it will donate that proton to ammonia, forming, as products, the ammonium ion, NH4 positive, and the chloride ion, Cl negative. And you can see here again how this is going to help us to minimize changes to the pH, because upon the addition of the strong acid HCl, the reaction which occurs has the net effect of turning that strong acid, HCl, into the product, the weak acid, which is NH4 positive. And as such, it would mitigate a large change in the pH of the solution. Likewise, if we consider what happens upon the addition of a strong base to our solution, the strong base sodium hydroxide will react to the acidic component of our buffer system. So upon the addition of sodium hydroxide to our solution, again, I don't really care about the presence of the sodium ions, as again, those are very, very weak conjugate acids of sodium hydroxide. So instead, what I'm interested in here is the addition of the hydroxide ion, which is the strongest base which can exist within an aqueous solution. Upon that addition of the hydroxide ion, it will react to the acidic component of my buffer system, which was the ammonium ion, NH4 positive. And in doing so, we would form the products here, which would be ammonia, NH3, and water, H2O. And again, you see the net effect of this process is to turn that strong base, the hydroxide ion, into the weak base, NH3, ammonia. And again, this would minimize the impact to the pH of the solution. So again, we can see that this effective buffer will work because it's able to both absorb hydrogen ions from an added acid and hydroxide ions from an added base, and in doing so, it changes the strong species into a relatively weak species, helping to maintain a relatively constant pH. All right, so we've seen it in action now. Let's take a look at some examples of which systems might be considered buffers. For example 2, we're going to ask you which of these following mixtures of solutions could act as buffer systems, and we want you to justify your reasoning for each of these potential buffer solutions. Now, remembering from our previous slide, a buffer is a system which contains both either a weak acid and the conjugate base of that weak acid, or a weak base and the conjugate acid of that weak base. So let's consider these solutions one at a time. The first of which is a solution containing a mixture of 1.0 molar hydrochloric acid and 1.0 molar sodium chloride. Now, right off the bat, I see some problems with this system. Primarily, number one, that the acid which is present in this system is a strong acid, that is hydrochloric acid. Now, that's going to create a problem for us when we look to the conjugate species which is present. The conjugate base of hydrochloric acid is the chloride ion, Cl negative. And we see that the chloride ion is present in our solution because it's present from the 1.0 molar NaCl. Now, this solution would be very, very effective at absorbing added bases, because I could write a reaction here in which the acidic component of my system, that is the acid HCl, would react to an added base, OH negative, to form water, H2O, and chloride ion, Cl negative. So that seems effective at absorbing base, but the problem is there's no component of the system that can effectively absorb an acid. That is, if I look to the base present in this system, that is the chloride ion, recall the chloride ion is the conjugate base of a very strong acid, implying, therefore, it is a very, very weak base. And weak bases are not effective proton acceptors. So were I to write a reaction here in which the chloride ion were to absorb a hydrogen ion that was added as a strong acid was added to the solution, the chloride ion plus a hydrogen ion would end up forming the product here of HCl, hydrochloric acid, which I know itself is a strong acid. And because strong acids completely dissociate into solution, that means that this reaction that I've written in the forward direction here does not meaningfully occur within the solution. And therefore, the chloride ion is ineffective at absorbing added hydrogen ions to the solution, and therefore would not resist changes to the pH of the solution upon the addition of more acid. So this mixture would not be an effective buffer. Now, conversely, let's take a look at the mixture described in the second description here. If we have a solution which contains a mixture of 1.0 molar carbonic acid, H2CO3, and 1.0 molar sodium bicarbonate, NaHCO3, recognize here, first of all, that carbonic acid H2SO3 is itself a weak acid. And then the salt here, sodium bicarbonate, NaHCO3, is a salt which contains here the conjugate base of that weak acid. That is the base HCO3 1 negative. Now, think for a moment again about what's going to happen in our system if we add either an acid or a base to this buffer mixture. Upon the addition of a base, if I add OH negative, the OH negative will be effectively absorbed by the carbonic acid H2CO3. And as we do so, we'll end up forming water and either bicarbonate ions or carbonate ions, CO3 2 negative. So we can effectively absorb hydroxide ions. But now consider where this differs from the previous example. What happens when I add an acid to the system? Upon the addition of an acid, I would generate additional hydrogen ions in solution. Those hydrogen ions in solution will react to the basic component of the buffer system, which is that conjugate base HCO3 1 negative. Upon adding H positive to HCO3 1 negative, you'll see here that we form as a product carbonic acid H2CO3. And again, we've now effectively absorbed those added H positive ions, forming, as a result, the weaker acid H2CO3. So this particular solution both has an effective means at absorbing hydroxide ions, that is the carbonic acid, and a means of absorbing added hydrogen ions, that is the bicarbonate ion. And as such, this can either minimize the impact of added acid or base, and will therefore be considered an effective buffer system. All right, so now we've seen which solutions can effectively act as buffers. That is, again, a solution containing both a weak acid and the conjugate base of that weak acid, or a weak base and the conjugate acid of that weak base. So now that we've seen this qualitatively, let's talk about how to quantitatively calculate the pH of a buffered solution. How these problems tend to go is as follows. We're going to start off by calculating the pH of the original buffer solution. This will require the use of an ice table. Recall, however, in a buffer solution, you will have two species present, that is, both the acid and its conjugate, or the base and its conjugate. Once you've calculated the pH of that original solution using an ice table, the next step is that you're going to go ahead and see the addition of either the strong acid producing excess hydrogen ions or a strong base producing excess hydroxide ions. At that point, you're going to write an equation describing the neutralization reaction that takes place with either the added acid or base and the component of the buffer system which is likely to react to that added acid or base. Assume in this process that the neutralization reaction will go to completion, because even though the components of the buffer system themselves are weak species, remember what we are adding to them is strong acids and bases, and strong species are fantastic donors or acceptors of protons, and as such, that reaction essentially will be assumed to go to completion. Now, recognizing that this is essentially a reaction that goes to completion, equilibrium measures are not appropriate for solving for the new concentrations of the ions present in the solution after this addition of acid or base. Instead, I would encourage you to use the stoichiometric relationships described by the neutralization reaction to calculate the new concentrations of all species using a device which we call an ICN table, which is similar to a standard ice table, but instead of finding equilibrium concentrations, instead it's just going to find the new concentrations after that reaction goes to completion. In general, when using these ICN tables, it is most effective to set them up using units of moles rather than using molarities of solution, because molarities might not be additive depending upon the volumes of the solutions which you mix together. So once we've determined the new concentrations of all species present in your system, at that point, you can now solve the equation using a new ice table with those new initial concentrations of the acid and conjugate base present in your system. From that new ice table, you can find either the new concentration of hydrogen ion or hydroxide ion, and from there calculate the new pH. So there is a sequence of steps we will follow. Let's take a look at this process in our next example problem. All right, and in this example number 3, we now come to kind of the big one for this lecture. We're going to be looking here at determining the pH of a buffer solution. Suppose we produce a buffer by mixing together a solution that generates 0.50 molar acetic acid, CH3CO2H, and 0.50 molar sodium acetate, NaCH3CO2. I'm going to want you here to calculate the initial pH of the solution, and then again to calculate the pH of the solution after the addition of 0.10 moles of the solid strong base sodium hydroxide, NaOH, to 2.0 liters of that solution. And as a given for you here, I'm supplying you with the Ka of the weak acid acetic acid, which is 1.8 times 10 to the negative 5. So again, in this process, the very first thing we want to do is to calculate the initial pH of our solution. And to do that, we're going to use a traditional method, which is an ice table. Now, the first thing I want to do is I want to write a reaction that governs the equilibrium present in this system, by starting off with the acidic component of the system here, which is my acetic acid. Recognizing that acetic acid is going to act as an acid, it will therefore dissociate to produce hydrogen ions in solution. So I'm going to write the equation here, which is CH3CO2H dissociates in an equilibrium state to produce hydrogen ions H positive and the acetate ion CH3CO2 1 negative. Now, with this initial reaction written here, I'm going to set up below it an ice table to determine the changes in concentration as this system establishes equilibrium. Plugging in my initial concentration given to me of the acetic acid of 0.50 molar, I'm going to assume here an initial concentration of hydrogen of close to 0 for the H positive ion, and then also recognizing that I have an additional component of the system here, that was the species sodium acetate, NaCH3CO2. Recall sodium acetate is a soluble salt, and as such, it completely dissociates into sodium ions and acetate ions. Now, I'm not interested in the acidic properties of the sodium ion because it is a very, very weak acid, but I am interested in that acetate ion, CH3CO2 1 negative, as that acetate ion, again, is the conjugate base of acetic acid. And again, recognizing that this dissociation is a 1-to-1 mole ratio, a 0.50 molar solution of sodium acetate generates in solution a 0.50 molar concentration of the acetate ion, which I'll now plug into my ice table under the initial concentrations. All right, so we've got all of the species present here and accounted for under initial concentrations. From this initial set of conditions, the only direction this system can shift as it establishes equilibrium is a shift to the right, because I have generally essentially no hydrogen ions in my solution. So as this shifts right, my changes in concentration will be defined as a minus X for the acetic acid, a plus X for the hydrogen ion, and a plus X for the acetate ion CH3CO2 negative, yielding me therefore equilibrium concentrations of 0.50 minus X for acetic acid, X for the hydrogen ion, and 0.50 plus X for the acetate ion. And with this ice table set up, this is now a familiar problem that you can solve using a Ka expression. By definition, again, the Ka is always the ratio of concentrations of the products over reactants, which for this equilibrium system would be the concentration of H positive times the concentration of CH3CO2 negative divided by the concentration of the molecular acid CH3CO2H. With this Ka expression now written, let's plug in the values which we are given within our problem. That is the Ka of acetic acid, which was 1.8 times 10 to the negative 5. That is equal to now hydrogen ions equilibrium concentration, which from my ice table here I find to be a value of X moles per liter, times the acetate ions concentration of 0.50 plus X moles per liter, divided by the molecular acid CH3CO2H's concentration, which I find at equilibrium to be 0.50 minus X moles per liter. And this setup for my ice table here seems like a great opportunity for me to simplify this expression so I don't have to solve a quadratic by making an assumption. I will go ahead and assume here that because my Ka value is very small, that implies that the given X values will also be very small, and as such, I will assume that the X value is very, very small compared to the initial concentration of 0.50. By making that assumption, my expression simplifies down to 1.8 times 10 to the negative 5 is now equal to my hydrogen ion concentration of X times 0.50 plus a very, very, very small x value, which essentially is close enough to 0.50 that I may assume it is so, divided by 0.50 minus a tiny number, which essentially simplifies down to 0.50 as well. And you'll notice here I now have simple algebra to solve. I'm just going to go ahead and cancel the 0.50 in my numerator and denominator, and I get now an x value which turns out to be equal to 1.8 times 10 to the negative 5 molar. At this point, we can go ahead and check our assumption. In checking my assumption again, I want to prove that my x value truly was small in comparison to the initial concentration of 0.50. So I'll divide my x value of 1.8 times 10 to the negative 5th by the initial concentration I assumed it was small in comparison to, which was 0.50 molar, and then multiply that by 100 to express this as a percentage. And you'll notice here that that percent error here turns out to be 3.6 times 10 to the negative 3rd percent, a tiny, tiny, tiny amount of introduced error in this system. So this is a safe assumption to have made. We've not introduced undue error to our calculation, so I can go ahead and proceed. Now that I'm okay with my solved x value, recognize from my ICE table that the x value is equal to the hydrogen ion concentration and equilibrium in this system. And as such, I can now solve for the pH of that solution. The pH would be equal to the negative log of my concentration of hydrogen ion of 1.8 times 10 to the negative 5, which yields a value in my calculator here of 4.74. So we have an initial pH of this buffer solution of 4.74. Now, up until this point, we've only dealt with a familiar system in which we've just calculated the pH of a solution using an ICE table. Let's now see how the system behaves as a buffer. Recall, buffers resist changes to their pH upon the addition of either a strong acid or a strong base. So in this system, we are going to be adding, again, 0.10 mole of solid phase sodium hydroxide, that strong base, to 2.0 liters of our solution. So at this point, we need to do a little bit of logical thinking in terms of the chemistry that's going to occur within the solution. The strong base NaOH is going to dissociate into sodium ions and hydroxide ions. That hydroxide ion will react to the acidic component of my buffer solution. So at this point, I'm now going to go ahead and write an equation that describes that neutralization reaction which is occurring within the buffer. So I'm going to go ahead and then write down here the acidic component of my buffer, which was the acetic acid, CH3CO2H, will react to the added hydroxide ions, OH negative, and as they react together, we're going to produce here the acetate ion, CH3CO2 negative, and water, H2O. And again, I'm going to assume that this particular reaction essentially goes to completion because even though the acid is a weak acid, the base which was added here, the hydroxide ion, is a fantastically strong base and as such is going to be great at ripping hydrogens off of those acetic acid molecules. So in setting up a table now, I'm not going to write an equilibrium table, an ICE table here. I'm instead going to essentially do a stoichiometry table here, which is an ICN table. And again, as we discussed on the previous slide, this is best dealt with in terms of units of moles. So let's take a look at the amounts of these species which are present, not the concentrations, but the amounts. I have, again, the 0.50 molar acetic acid, and there are 2.0 liters of this solution. So multiplying 2.0 liters by 0.50 moles per liter of the acetic acid, that will cancel out those units of liters for me, yielding 1.0 moles of acetic acid in my solution itself. So I'll enter that into the initial amounts in my ICN table. There is additionally 0.50 molar sodium acetate, which yields 0.50 molar acetate ions in the buffer solution as well. And by that same logic, 2 liters of solution times 0.50 moles per liter yields also 1.0 moles of acetate ions in my solution as well. So I'll plug that value into my ICN table as well. And now, from the givens in the problem, we are adding 0.10 moles of solid sodium hydroxide to this solution, which would yield 0.10 moles of hydroxide ions, as that sodium hydroxide also dissociates in a 1-to-1 ratio to form hydroxide ions. And at this point, I'm going to look at my setup, recognize here, folks, that the hydroxide ion is clearly going to be the limiting reagent in this neutralization reaction as it goes to completion. So I'm going to assume then that all 0.10 moles of the hydroxide ions will be consumed over the course of that reaction. And as we do so, I'll also consume 0.10 moles of the acetic acid as they react to hydroxides in a 1-to-1 mole ratio, simultaneously producing 0.10 moles of acetate ions as products of that neutralization. So therefore, I can now calculate my new amounts of both acetic acid and acetate ions which are present in the system. For the acetic acid, we started off with 1.0 mole. We consumed 0.10 mole, yielding now a new number of moles of 0.90 moles of acetic acid. And likewise, all of the hydroxide ions will be consumed, leaving me with essentially none left on my reactant side. On the product side, we started off our buffer system with 1.0 mole of the conjugate base CH3CO2 negative. We produced 0.10 more mole of that species over the course of the reaction, and we now have, therefore, 1.10 mole of acetate ions present in our solution. So we now know the new amounts of both the acid, acetic acid, and the conjugate base, the acetate ion. Let's now calculate their new concentrations and then use them to solve a new ice table. By definition, again, molarity is moles per liter. So for the acetic acid, we now have a new 0.90 moles of acetic acid dissolved within our now 2.0 liter solution, which yields for me here a 0.45 molar solution of acetic acid. Likewise, the molarity of the acetate ion can be found by dividing the 1.10 mole of acetate ions by the 2.0 liter solution to yield a 0.55 molar solution of acetate ions. So now that I know the concentrations of both the acid and the conjugate base, we can revisit an ice table now and solve for the new hydrogen ion concentration present in our system. So going back to the original equilibrium we were dealing with in our buffer system, acetic acid CH3CO2H dissociates to produce hydrogen ions in solution and acetate ions CH3CO2 negative. And let's solve now a new ice table. Setting up our new ice table, the initial concentration of acetic acid is now 0.45 molar. Of hydrogen ions, again, we'll assume close to 0. And of acetate ions, we are now the new concentration of 0.55 molar, which we have just solved for. This system will still shift to the right as we establish equilibrium, yielding changes in concentration of minus X for acetic acid, plus X for hydrogen ions, and plus X moles per liter for acetate ions, yielding equilibrium concentrations of 0.45 minus X molar for the acetic acid, X moles per liter for hydrogen ion, and 0.55 moles per liter for the acetate ion. And from this point on, this is stuff you know how to do. We can now again solve for X using a K expression. The Ka for my acid, as we saw before, is the ratio of concentration of products over reactants, that is H positive times CH3CO2 negative divided by CH3CO2H. Plugging in the equilibrium concentrations here into my expression yields the value here for my Ka of 1.8 times 10 to the negative fifth is equal to hydrogen's concentration of X moles per liter times the acetate ion's concentration of 0.55 plus X moles per liter divided by the acetic acid's concentration of 0.45 minus X moles per liter. And just like we did before, we're now going to simplify this by assuming that the X value is very small compared to that initial molarity of the acid of 0.45. As I make that assumption, my new expression simplifies down to 1.8 times 10 to the negative fifth, my Ka value, is equal to X times 0.55 plus a tiny number, which essentially is 0.55, divided by 0.45 minus that tiny number, which is close enough to 0.45 that we may assume that that is its value. And again here, all I have to do is algebraically solve for X. I'll multiply both sides by 0.45, divide by 0.55, and this yields for me here an X value of 1.5 times 10 to the negative fifth. Making sure to check my assumption to prove the assumption was valid, we will go ahead and divide that X value of 1.5 times 10 to the negative fifth by the value I assumed it was small in comparison to, which was 0.45 molar, and multiply it by a factor of 100 to express it as a percentage. And as I do so, I calculate a percent error here of 0.0033%, which again is well within our 5% range that we accept as valid. So our assumption seems to be A-OK. All that remains now is cleanup here. I can find my pH of this solution, recognizing the X value from my equilibrium expression was the concentration of hydrogen at equilibrium. At pH would therefore yield the minus log of the X value of 1.5 times 10 to the negative fifth, which when I plug into my calculator, I get here a value of 4.83. And now that we've done the math, let's take a moment to see how this system is effectively acting as a buffer. We started off with the solution, again, at a pH of 4.74, and to that solution, I added a fairly large amount of a very strong base, sodium hydroxide. Now, had this been a regular old solution, that addition of the strong base would have caused its pH to skyrocket. But notice here, as that base was added, it was consumed by reacting to the acetic acid in the solution, and the net effect of that was that the new pH of the solution after the reaction had occurred only increased from 4.74 up to a new pH of 4.83. A very small change in pH given the amount and the strength of the base that we have added to this system. So you can see here then that this system effectively absorbs the addition of a strong base and therefore is an effective buffer system. Now that is a lot of math to do to get to this final answer here. On our next slide, we will see a shortcut that will make your life much, much easier. All right, so now that we have seen the kind of long and involved process of solving a complete buffer problem, we are going to make your lives a little bit easier here on this next slide and develop an equation that is going to be very useful in terms of shortcutting to a pH of a buffer solution. So this is what we refer to as the Henderson-Hasselbalch equation, and we're going to like this one. This one's going to be our best friend for dealing with buffers. A manipulation of the Ka expression, that is the Ka of a weak acid concentration of H positive times A negative divided by HA, can be useful here in a quick rearrangement of the equation. So let's go ahead and take that generic expression for a Ka of a weak acid and rearrange it to solve for the concentration of hydrogen ion H positive. So to isolate H positive by itself here, I'm going to multiply both sides by the concentration of HA and divide by the concentration of A negative. And that yields for me here this new expression, which is the concentration of hydrogen ion H positive is equal to the Ka of our weak acid times the concentration of the molecular acid HA divided by the concentration of the conjugate base A negative. And now that I have it in this position, I'm going to go ahead and take the negative log of both sides of that equation. And in doing so, we're going to go ahead and apply a couple of our log rules here. So again, by taking the negative log of both sides, I get on the left side of my equation the negative log of the concentration of H positive. And then on the right side of the equation, recall for a moment here, folks, that from your log rules, the log of a product, that is A times B, is equal to the log of A plus the log of B. So I'm going to go ahead and apply that log rule here, recognize again that this is a negative log, which I've taken here. So as I do so, I'm going to go ahead and simplify that down with the new expression being on the right side of my equation, the negative log of the Ka, and then minus the log of the ratio concentration of H positive divided by the concentration of A negative. And now that I've done that, I'm just going to do a real quick rearrangement again to get rid of the negative there at the end of my expression. And applying a second log rule here, we get a new expression here, which is the negative log of H positive is now equal to the negative log of the Ka, and then plus, I'm just going to invert that there, plus the log of the ratio of A negative divided by concentration of HA. And what we've just developed right there is what we refer to as the acidic version of the Henderson-Hasselbalch equation. Recognizing again that the left side of my equation, the negative log of concentration of H positive, by definition, is the pH of the solution, and the negative log of the Ka value is, by our definition, the pKa of that acid. So what this really tells me then is that I can find the pH of a solution here if I know the Ka of the acid involved in the buffer system and the concentrations of the conjugate base A negative and the acid HA, which are present in my solution. And that's a very, very useful tool for me here, which means I can essentially cut out the entire step of solving at any point an ice table. And this seems like we're kind of simplifying things past where we should be able to do so, but remember, in these ice tables for a buffer system, the X value tends to be a very, very, very small change in concentration of the acid over the course of the reaction. Because, number one, it's a weak acid in the system to begin with, and so therefore we would expect to see a small x. But number two, the common ion effect of the presence of that conjugate base A negative has the net effect of driving the equilibrium to the left in the dissociation equation of that acid, and as such, the X value is even smaller than it otherwise would be if it was a pure acid solution that we were dealing with. And as such, this system is essentially going to be able to be solved without an ice table because we always assume the X value is so small as to be essentially meaningless, which means I can essentially assume the initial concentrations of the conjugate base A negative and the acid HA are more or less equal to their equilibrium concentrations as the system establishes that equilibrium. So I just saved myself a tremendous amount of work there without having to solve the ice tables for determining a pH of a solution. Now, likewise, if I have a buffer system which is made up of a weak base B and the conjugate acid of that base HB positive, I could go through the exact same logical sequence of steps. Rather than starting with the Ka of the acid, instead I would start with the Kb of the base and do the same rearrangement to the equation to solve for the concentration of hydroxide ion and taking again the negative log of both sides. If I go through that process, I now get a version of the Henderson-Hasselbalch equation for a basic solution, in which we can calculate here the pOH of the solution is equal to the pKb of the base plus the log of the concentration of the conjugate acid divided by the conjugate base. So again, this will simplify my life, allowing me to avoid having to solve an ice table. So let's go ahead to our next slide. And on the next slide, we're going to take a look at an example problem in which we are going to use the Henderson-Hasselbalch equation to rapidly determine the pH of a buffer solution. All right, so in this example problem, we're essentially going to attempt to show how much more efficient the Henderson-Hasselbalch equation can be when dealing with buffer systems. We are going to take here a buffered solution which has been prepared to produce 0.40 molar solution of ammonium chloride and 0.25 molar ammonia. And with this solution, we're going to calculate the pH, first of all using the ice table method, and then after that we will show the same procedure but solving instead with the Henderson-Hasselbalch equation. And as a given value here, we're providing you with the Kb of ammonia, which is 1.8 times 10 to the negative fifth. So let's first go ahead and solve this using the familiar ice method. Starting off with our equilibrium system, we have ammonia, which is again a base. So we're going to show ammonia acting as a base within an aqueous solution, accepting a proton from water. And as products of that reaction, we would therefore form the ammonium ion, that is the conjugate acid of ammonia, NH4 positive, and hydroxide ions, OH1 negative. So here's our hydrolysis reaction. Let's now go ahead and set up an ice table. We have been given here an initial concentration of ammonia of 0.25 molar, and then 0.40 molar ammonium chloride, recalling from our solubility rules that all ammonium compounds are soluble. That means, therefore, that ammonium chloride will completely dissociate into ammonium ions and chloride ions, and therefore I'm safe to assume here a concentration of ammonium ion of also 0.40 molar. And we'll assume a value of close to 0 for the hydroxide ion initially present in our system. All right, now from this initial set of conditions, we're going to go ahead and determine the change in concentrations as we approach equilibrium. This system must shift to the right as we've got a 0 there for hydroxide's concentration, implying therefore my changes in concentration will be a minus X moles per liter for ammonia, plus X moles per liter for ammonium ion, and plus X moles per liter for the hydroxide ion, yielding therefore equilibrium concentrations of 0.25 minus X moles per liter for ammonia, 0.40 plus X for ammonium ion, and X moles per liter for the hydroxide ion. All right, so we've got an ice table set up. We know how these processes go at this point. We can go ahead now and set up our Kb expression. As always, products over reactants yields a Kb of the concentration of ammonium ion, NH4 positive, times the concentration of hydroxide ion, OH negative, all divided by the concentration of ammonia, which is NH3. And we will now plug in our given values here from both our ICE table and the Kb given to me in the problem. My Kb was given as 1.8 times 10 to the negative fifth. That is equal to my equilibrium concentration of ammonium ion, which we said was 0.40 plus X moles per liter, times the hydroxide concentration of X moles per liter, divided by ammonia's concentration of 0.25 minus X moles per liter. And at this point, it seems quite safe to make an assumption here, given a very small value of K. We will assume that the X value in this equilibrium system is very small compared to the smallest initial concentration of 0.25 molar. That will then simplify my expression down to 1.8 times 10 to the negative fifth is equal to 0.40 plus a tiny number, essentially is 0.40, times my X value, divided by, in the denominator, 0.25 minus X will simplify just down to 0.25 molar. And from here, I'm happy to solve. We can go ahead and calculate my X value by multiplying both sides by 0.25 divided by 0.4. And that yields for me here an X value of approximately 1.1 times 10 to the negative fifth molar. And again, because I made an assumption, I need to prove that assumption valid. We will check the assumption by dividing the determined X value by the initial concentration we assumed it was small in comparison to. So my 1.1 times 10 to the negative fifth divided by 0.25 molar times 100 to express that as a percentage yields for me here a percent error introduced of 0.0045%, well below the 5% range we assumed was valid for our calculations. All right, so we've got an X value. Now it's just clean up from here. We can now calculate our pOH of the solution, because from my ICE table, note that the X value is the concentration of hydroxide ion. The pOH will be the minus log of my X value of 1.1 times 10 to the negative fifth, and plugging that into my calculator, I find a value here of 4.95 for the pOH of this solution. And a quick pH calculation from there, 14 minus my pOH will yield my pH. 14 minus that 4.95 yields a pH of 9.05. All right, so we now have a pH of our solution solved via ICE table. Now let's go ahead and do it with the Henderson-Hasselbalch equation so we can see how much more efficient this truly is. Because I am dealing here with ammonia as a component of the buffer, I'm going to set up the basic version of my Henderson-Hasselbalch equation. And from our previous slide, recall that that was the pOH of the solution is equal to the pKb of the base plus the log of the ratio of the conjugate acid, which in this case is the ammonium ion, NH4 positive, divided by the base, which was in this case ammonia, NH3. And at this point, we can go directly to plugging in some values here. My pKb would be, by definition, the minus log of the Kb value, in this case of 1.8 times 10 to the negative fifth, plus that log of the ratio of ammonium over ammonia. That would be the log of a concentration of 0.40 molar for the ammonium ion, divided by 0.25 molar for our ammonia. And again, I can just directly plug this into my calculator, and lo and behold, I find here a pOH exactly as we expected of 4.95. And that means I can find my pH now by again taking the 14 minus 4.95, yielding a pH exactly as we had calculated before of 9.05. So you can see we end up with the exact same results, but without having to solve the entirety of the ICE table, which simplifies and saves me a lot of time, which is a very, very valuable resource on your AP test. So I would encourage you on that AP test to, if you're dealing with the buffer system, think first and foremost to the Henderson-Hasselbalch equation, whether it is appropriate. Now, you got to be careful because in some years they have given you the Henderson-Hasselbalch equation on the test itself in the equation sheet. On other years, they have not. So I would strongly encourage you to memorize this equation, as it is a very, very useful tool to have in your repertoire. All right, now on our following slide, we're going to look at an extension of this problem to see again how Henderson-Hasselbalch can also be used to show the buffer in action. And we'll have a look there next. All right, in this last example problem, we are going to start with the same buffer solution which we described on the previous slide in example 4, and now determine the new pH of the solution after the addition of 0.10 mole of hydrochloric acid to 2.0 liters of the solution, assuming we experience no change in volume. So as a starting point here, let's consider how our buffer system will react upon the addition of the hydrochloric acid to our system. Hydrochloric acid, as we know, is a strong acid, and as such, it will be expected to interact with the basic component of our buffer, which from our buffer system, recall, was the ammonia. And as such, I'm going to go ahead and write a reaction describing the reaction between the hydrochloric acid and ammonia. Recognizing again that hydrochloric acid is a strong acid, it should exist essentially as dissociated hydrogen ions and chloride ions. That chloride ion is going to be a spectator, so I'm going to go ahead and ignore it here and just skip straight to the net ionic equation in which ammonia, NH3, will accept the proton H positive from the hydrochloric acid to produce ammonium ions NH4 positive. And again, recognizing that the hydrochloric acid, again, is a strong acid, I'm essentially going to assume that this reaction goes more or less to completion within our solution. And as such, I'm going to set up, rather than an ICE table here, an ICN table to determine the new amounts of both ammonia and ammonium present in the system after this reaction occurs. Recall in our ICN tables, we want to be dealing with units of moles rather than molarities. So I'm going to first calculate the number of moles of both ammonia and ammonium ion in my system. Because molarity, again, is moles divided by liters, I can find moles by multiplying the molarity of the solution by the volume in liters, which for my ammonia, NH3, would be 0.25 molar times the 2.0 liters, which yields here 0.50 moles of ammonia present in my solution. So I'm going to put that as the initial amount of ammonia, NH3, in my ICN table. Same equation for the calculation of moles of ammonium ion. The ammonium ion was a concentration of 0.40 molar, and again, 0.40 molar times 2.0 liters yields 0.80 moles of ammonium ion NH4 positive, which I can also place in the initial conditions of my ICN table. Now, recall again, from the givens in the problem, I was adding 0.10 mole of hydrochloric acid, which would again dissociate to produce 0.10 mole of hydrogen ion to this system. So I'll put that as my initial conditions here. And as we can clearly see in this ICN table, the hydrogen ion H positive is going to act as the limiting reagent in this reaction. So I can assume all 0.10 mole of hydrogen ion will be consumed as this reaction goes essentially to completion. So I'll have minus 0.10 mole of my reactants, NH3 and H positive, and I would see a plus 0.10 mole of the ammonium ion produced on the product side as this reaction occurs, yielding new amounts present of 0.40 mole of ammonia, NH3, 0 for my hydrogen ion, and 0.90 moles for the ammonium ion, NH4 positive. So I now know the new amounts of both ammonia, NH3, and ammonium ion, NH4 positive in my system. I can now apply the Henderson-Hasselbalch equation again, recognizing again that the Henderson-Hasselbalch equation uses molarities. I need to recalculate my new molarities of both the base and its conjugate acid. For the molarity of ammonia, NH3, I now have 0.40 moles in the 2-liter solution, which yields a molarity of 0.20 molar. And for the ammonium ion, NH4 positive, I now have, under my new conditions, 0.90 moles in the 2.0 liters, which yields a 0.45 molar solution of ammonium ion. With these new calculated concentrations, let's now use our Henderson-Hasselbalch equation to find the pOH of our solution. Recall this for a basic solution, the pOH will be equal to the pKb of the base plus the log of the ratio of the concentration of the conjugate acid, in this case NH4 positive, divided by the concentration of the base NH3. And plugging in from my calculations now, let's see, the pKb would be the minus log of the Kb value of 1.8 times 10 to the negative fifth, plus the log of the ratio of ammonium's new concentration, which was 0.45 molar, divided by ammonia's concentration, which was 0.20 molar. And as I plug these values into my calculator here, I get a pOH of 5.10. And then from that, I can rapidly calculate a pH here by taking 14 minus my pOH, which yields here a pH of 8.90 in this system. So you can see how much faster that was now, again, than solving multiple ice tables here by using that Henderson-Hasselbalch equation, a much, much friendlier and more efficient pathway. And also we note here that this system was effectively working as a buffer, because recall my initial pH of the solution was 9.05, and upon the 0.10 mole of the strong acid HCl being added, it only decreased that pH from 9.05 down to 8.90, showing again that the system effectively absorbed the addition of hydrogen ions without meaningfully changing the pH of our solution. All right, so that's how these problems tend to work. Let's take a look at one more conceptual idea before we finish up this lecture. All right, for our final slide in the buffer lecture here, we're going to talk about a type of question that tends to show up both on the multiple choice section as a conceptual question and in the free response section on AP Test. And that is how to select an appropriate buffer for a given situation. Now consider for a quick moment here, folks, if we want to have an effective buffer, that buffer again needs to be able to absorb both added hydrogen ions and hydroxide ions to the system without meaningfully changing the pH of the solution. And you can imagine a scenario in which I had, let's say, a concentration of 0.0001 molar for both the acidic and basic components of a buffer system, with very, very low concentrations of the species present in that buffer. If I add either hydrogen ions or hydroxide ions in high enough amount, those hydrogen and hydroxide ions will essentially consume the entirety of the components of the buffer, and as such, at some point, you'll run out of the ability to absorb those hydrogen or hydroxide ions as they're added. We call this process exceeding the buffer capacity. And once the buffer capacity has been exceeded, any additional hydrogen or hydroxide ions added to the system will essentially go directly into the solution without being absorbed, and as such, the buffer no longer functions. So first off, to have an effective buffer, we need to make sure that we have a sufficient number of moles of both the conjugate base A negative and the weak acid HA in order to absorb any added acid or base in our system. So that's a primary thing we look for a functional buffer. Now, another thing that makes buffers function properly is that they might have a ratio of the conjugate base A negative to HA, which is a close to 1-to-1 ratio. That really means that the buffer will both be effective at absorbing both base and acid whenever those are added to the system. And importantly here, if we look at that 1-to-1 ratio of the conjugate base A negative to the acid HA, that would tell me something meaningful if I look at a little bit of the math here. The pKa of the acid component of our buffer should be hopefully very close to the desired pH that I want to buffer my system around. And we can see why that works from the math. If we have a look at our Henderson-Hasselbalch equation here, recall that the pH of a solution is equal to the pKa of the acidic component of the buffer plus the log of the ratio of the conjugate base A negative divided by the concentration of the molecular acid HA. And again, assuming that we have a properly designed buffer, recall that ratio of A negative over HA, we said we want to be as close to 1 as possible. So if I plug in a value of 1 for the ratio of concentration of A negative over HA, my Henderson-Hasselbalch equation simplifies down now to pH is equal to pKa plus the log of that ratio, which we said we want to be equal to 1. And recall that the log of 1 is equal to 0. And as such, that tells me that the pH of that solution would be equal to the pKa of the acidic component of the buffer. Now, as it turns out, this is super useful in the real world because that really allows me to select an appropriate acidic component of a buffer to help me to control the actual pH around which the solution is buffered. And to give you an idea about where we actually might see that in the real world, consider your bloodstream. It's very important that your blood maintain a pH very, very close to a value of around 7.4 for your cells to effectively function and not die. And as such, the blood is effectively buffered by a system primarily composed of carbonic acid, H2CO3, and the bicarbonate ion, HCO3, 1 negative. Now, that particular acid-base combination yields a pH close to 7 when we have that buffered system because of the Ka of carbonic acid, which is a value approximately equal to 4.5 times 10 to the negative 7th. Now, that's effective at buffering your blood within that narrow range, right around 7.4 or so, whereas a different acid, like say acetic acid with a Ka of 1.8 times 10 to the 5th, would produce a buffer system of much too low a pH for your body to properly function. So a chemist can select an appropriate buffer to maintain an appropriate pH range around a particular value by simply selecting an appropriate acid and base combination, knowing the Ka of the acid and the Kb of the conjugate base. So, in summary, an effective buffer will have a sufficient amount of moles of both the acid component and the base component to absorb any added acid or base present in the system without exceeding its buffering capacity. And we should see a pKa of the acid which is close to the actual desired pH of the system around which we wish to buffer. All right, that is buffers. Thank you very much for listening. We'll see you on the next lecture.